As the climate crisis has jumped to the forefront of mainstream conversations, it has provoked the construction industry into some soul searching to try and reduce its own carbon emissions. Architectural offices across the world are being increasingly asked to assess their project's carbon footprint, but often there are misconceptions and a lack of clarity as to what that exactly entails. My name is Stefanovic. I'm an architectural technologist and senior architecture industry specialist at Vectorworks, and I will try to help you understand carbon assessment in architectural projects.
So to start, I'd just like to talk about the landscape that we find ourselves in the context of today. So as everyone's been well aware of, climate emergency has constantly been over the news, as has the necessity of reducing our carbon footprint and reducing the global temperatures in an effort to combat climate change. Various initiatives, regulations, guidelines, codes, and so on have been put in place with the goal of trying to regulate the carbon emissions and to force developers and architects to reduce the impact of their buildings on the environment. So, for example, the recently released London Plan of 2021 includes a policy which requires all schemes that are being referred to the mayor to include whole lifecycle carbon assessment. For example, Royal Institute of British Architects has its own 2030 climate challenge, which sets out targets for reduction in embodied carbon and operational energy emissions for 2025 and 2030, and those targets are in line with the London Energy Transformation Initiative, another body which is trying to regulate or stimulate the stakeholders to reduce their carbon footprints. American Institute of Architects has its Blueprint for Better campaign, and Carbon Leadership Forum has the Carbon Challenge. There are other codes. You can see some here, and it's only a matter of time before this becomes a hard and fast commitment and before every new project and every retrofit is obliged to meet certain targets. So what is embodied carbon? What is whole lifecycle carbon assessment? First of all, stages within project lifecycle include cradle to gate, that deals with the extraction and production of raw materials into construction materials and products. Then cradle to completed construction involves the transport from factory gate to the construction site and then the construction process itself. We have use stages, which in the case of whole lifecycle carbon assessment include in-use emissions, maintenance, repair, replacement, and refurbishment. To complete the cradle-to-grave life cycle with stage C, end of life, which includes deconstruction, demolition, waste processing, and disposal. Also, the whole life cycle of carbon assessment can include stage D, or beyond system boundaries, and that includes reuse, recovery, and recycling, but also carbon sequestration. Okay, so how does one go about calculating embodied carbon? There are different calculation methods. The one acknowledged in the UK as the industry standards and used across the world as well is the method set out in Royal Institute of Chartered Surveyors professional statement and their whole life cycle carbon assessment for the built environment. That document sets out the methodology for obtaining material quantities and for assessing the carbon emissions at every one of the stages during the project lifecycle. AIA and Carbon Leadership Forum have embodied carbon toolkit for architects, which set out a similar process for measuring embodied carbon. And just as important are data sources, because how do we know how much embodied carbon there is in a material such as a brick or gypsum plasterboard, for example? There are data sources which are accepted worldwide, like for example the Inventory of Carbon Energy database done by University of Bath in Circular Ecology. That is an open source database which is looking at a statistical analysis of the market to derive an average embodied carbon factor for some of the most commonly used materials in construction. Around 200 default Vectorworks materials have embodied carbon factors from this database, and we keep adding to it. Those values are for a generic material, like a brick, or softwood timber, aluminium, and so on. There are many other databases, such as, for example, the EC3 tool by Building Transparency, which is a free database of environmental product declarations. Now, those relate to specific products and contain specific embodied carbon factors for those products as opposed to generic ones. For example, while assessing through the early stages, we can use generic values for gypsum plasterboard, but as soon as we know exactly which gypsum plasterboard we are specifying for the project, we should use the environmental product declaration values for that specific product. Okay, let's have a look at how this is implemented on a project in practice. We're going to assess this on this building model. As you can see, it's a fairly common single-family home in brick cavity wall construction with traditional components and materials used. I've tried to keep it as typical as possible, so it's basically business as usual. We're going to start from very early concept design stages, and what I've done is very quickly model up a house, and in terms of Vectorworks approach, I've used the modeling tools, which means I haven't used any walls, slabs, windows or doors, no parametric and advanced architectural tools, because I wanted to show how free modeling approach can be used in the very early stages. As you can see, the objects in my model are either generic solids or solid subtractions, there are some extrudes, and so on. To be able to assess the embodied carbon, the first thing that I need to do is obtain material quantities in my model. The best way to do this in Vectorworks is to make sure my elements are wherever possible using materials. As you can see, I am using materials for all of these objects. Materials are a type of resource within Vectorworks, and you can find them in the Resource Manager as a separate category. They're similar to classes in a way. They can be used to define the graphic attributes of the object they're assigned to, but the advantage of materials is that, unlike classes, they can hold data. There are two basic types of materials in Vectorworks: simple and compound. Simple materials are what you would think of when talking about materials. So for example, brick, plasterboard, mineral wool insulation, and so on. Compound materials are containers for two or more simple materials, defined by the proportion of each simple material within the compound material. And examples of compound materials would be reinforced concrete, insulated metal or timber studwork, brick and mortar. Let's have a look at the material properties. We can assign the graphic attributes like in classes, 2D fill, and surface textures. I can report the material as a volume or an area, and for embodied carbon calculation purposes, we will need to have volume checked here. I can define the product data for the material, classification details, cost, and then I can assign a bunch of physical properties to it as well. These are the key ones that we will be needing for our embodied carbon assessment: the embodied carbon and density of the material. In addition to that, I can assign a custom record format to my materials. Record formats can store a wide range of data about an object or symbol, and their data fields can be completely user-defined. Records can be attached to any object or symbol definition, and record values can be individually changed for each object or symbol instance to which the record is attached. Embodied carbon sheet record format has been created to support the calculation and should be attached to materials and objects in the model that will be assessed. It has custom fields such as product name, description, density, weight, embodied carbon factor, source, and others, but we'll talk about them more in detail when we get to the actual calculator. Seeing as we're still in the early design stages and I'm simply using objects like extrudes and generic solids, which means I'm not using walls, roofs, and slabs, I can't use the benefit of having components. So I can't have different materials within one building element like wall, or within this free model geometry which is simulating my walls, it would sort of be defeating the purpose of quickly modeling something like this up if I were to now have to duplicate or offset in order to properly simulate the components. I might as well be using walls and windows, but I really want to be able to model something like this very, very quickly. So what I can do is use a little trick to simulate this. I can create a series of compound materials. I've called them concept materials, and I'll show you exactly what I mean by that. So my concept external material is actually a compound material in which I can define a number of constituent simple materials, and I can define percentages for those materials for each one of them. We are in the early stages, and I'm okay with these percentages not being 100% accurate, but if you wish to be, you can calculate exactly what percentage of total wall volume is brick, how much is block, insulation, and so on. I've put approximate 30% for bricks, 30% for a block, 20% for the insulation, 15% for cavity, and so on. What is great about this is you only have to create these concept materials once, work out the accurate percentages, save the resources to your Office resource library, and use the same materials on your next project. So basically, when I query my model for the volumes, it will give me the total volume of all of these external walls multiplied by a factor of 0.3, and then that will be the total quantity of brick as a material in my model. I can also employ different kinds of strategies there. So for example, at my first floor, I have two different types of floor finishes. I have an external timber decking and I have interior wood flooring. So I can separate that out. And I can say, well, 5% of my total slab is going to be timber decking and 3% is going to be my wood flooring. If, for example, I have a bathroom inside there, I can further separate this 3% and say 2.5% is going to be wood flooring and 0.5% is going to be floor tiling, and so on. And then finally, I have concept window. So I have defined that as glass and 10% aluminium, and I have just created some. I've punched some holes in my exterior walls and I've filled those holes with simple extrudes which are 10 mm thick. Like I said, very, very simple, very, very early stage model and very approximate numbers for my material composition. Okay, so to begin with, let me introduce Vec and give you a tour around the calculator. You can find it under Tools, Reports, Pre-formatted Report, Embodied Carbon Calculator. You can also download the file containing the worksheet, some resources like materials and record formats, together with a user guide document which explains how to use the calculator. This file is found on Vectorworks University. If you just search for Vectorworks Embodied Carbon Calculator, it should come up. The worksheet is organized by two columns into project lifecycle stages. From left to right, we have the product stage, or cradle to gate, followed by the transport stage, the use stage for replacement, and the end-of-life stage for waste processing for reuse, recovery, or recycling and disposal emissions. At the foot of the worksheet, there is the construction stage, operational energy, which is slightly different and not part of this calculation, but rather the number is directly taken from Energos results, which we will see later. There is also end-of-life stage for deconstruction and demolition. You can also do some benchmarking for REBA 2030 climate challenge based on the results. And just to mention, there are a few notes and guidance columns which basically tell you what needs to be input for VEC to perform the calculations. There is another level of organization to the calculator, and that is by rows into materials, doors and windows, and single objects. This is also a hierarchical order of automation in embodied carbon assessment, meaning that using materials would be the most streamlined workflow to obtain embodied carbon values. Doors and windows are separate in this calculation because these objects don't support materials. We'll talk more about these in developed project stages later on. Finally, we have single objects, which could be specific items for which we have manufacturer's data on embodied carbon on a whole item level. Items such as sanitary ware or mechanical equipment, like a radiator or oven would be a good example. Okay, so as we already talked about, materials are the main way to obtain quantities from the Vectorworks model. In terms of input, we can look at the instructions. First input is yes or no. Do we want to use compound materials for quantities? Let's start from simple materials, and we'll get to compound in a minute. So we'll say no here, and I'll simply copy and paste or type in the name of the material where it says enter material name. The only thing to be aware of is that you need to input the name exactly as it is in the resource manager. We can consider two different approaches for compound materials based on available embodied carbon values from databases such as ICE. Let's first take insulated timber stud-work, for example. You will find EC values for softwood timber and PIR insulation as separate entries in ICE database or in a manufacturer's EPD. We would have insulated stud-work compound material assigned to a wall component, with percentages determining proportion of each simple material in the total volume. And then we can treat it as a simple material in VEC. Volume calculation will automatically apply the percentages to work out the correct quantity for timber and insulation separately. Some Vectorworks compound materials, such as reinforced concrete or bricks and mortar, are treated as special cases because databases such as ICE provide the EC values for such materials as a single material. We solve this in the VEC by allowing you to specify one material for the volume calculation and another for the EC value. In this example, we have the default Vectorworks compound material for reinforced concrete assigned to our wall. So we will say yes here and paste compound material name here. And we will use the EC value from the simple concrete material and paste the name here. This provides a great deal of flexibility when dealing with different EC databases. That's it, really. The key is to have the material properties populated. Embodied carbon and density are the ones that are required for the product stage. Volume quantities are being obtained directly from the model, and then weight and total embodied carbon for the product stage of the material is then being calculated from there. In order to allow for more space to populate with all the materials from your model, simply insert more rows. After that, copy the cells. We can remove the material name here so it stays blank and ready for a different material. Then copy the database header. Entire guide notes column can be hidden for presentation. Also these input rows, so we get a much cleaner look for presentation purposes. Moving on to the transport stage, the only input we need to assess emissions at this gate-to-site stage is material sourcing. In terms of input, it's similar. We need to input sourcing in here in material properties under construction and product source. Now there are some nominal transport scenarios defined in the RICS document that I mentioned earlier. Depending on proximity of the manufacturing site to construction site, it can be national, local, European, or global. Be careful to spell the words correctly for the calculation to work. There is also scope to enter a custom distance if we know exactly where the material is being manufactured and how far is that from the site. Just enter the word custom, then go to the embodied carbon sheet record format and input the custom transport distance here, being careful that you have custom selected in this drop-down. These transport scenarios can be changed. If you select the database header, you can change the nominal values. I can change national not to be 300, but to be 400, and I can change, for example, European to be American. This is a way to localize these values for different parts of the world if there is such guidance. You could also define your own transport scenarios, for example, in an accompanying document and have, for instance, transport scenario T1 as 100 kilometers, T2 as 500, T3 as 1000. Use stage uses replacement categories, which are again defined in the RICS document that lists the expected number of material replacements over the building lifespan, which is assumed at 60 years. Replacement category is selected in the embodied carbon sheet record format. So for example, in that document you can find 30 years as expected roof covering replacement, or for example bricks, you're never going to replace that as it's part of the external wall, so that's then none. And at 0, there is no replacement embodied carbon emissions. Finally, this stage deals with emissions relating to disposal of building materials and elements in their entirety, or parts that will not be repurposed. Waste percentage is the required input and is related to those end-of-life scenarios where a number between 0 and 1 is required. 1 means complete disposal of material, and that's the default value as recommended in absence of more specific data. That means that at the end of the life of building, the entirety of the material is going to be disposed of at a landfill. For example, if 40% of the material is going to the landfill and 60% of it is going to be recycled, then I can add that in my custom fields as 0.4 in there. And then basically that means that 40% of my timber stud work at the point where the building is being demolished and this material is being disposed of, 40% of it is going to the landfill and 60% of it is going to be recycled and reused elsewhere. Construction stage works on the basis of the project value. It's a UK-based estimate from the RICS methodology, where the embodied carbon for construction site emissions is estimated at 1400 kilograms per CO2 emissions for every £100,000 worth of project. So you simply enter, say, 750,000 for the value of my project, and then you get your total embodied carbon for construction emissions. Similarly, end-of-life stage for deconstruction and demolition works off of gross internal area, so embodied carbon for all deconstruction and demolition related activities is given as 3.4 kilograms CO2 equivalent for meter square of gross internal area. So we simply need to input gross internal area here, for example 150 meters square, and we can see the total deconstruction and demolition emissions from there. This is a very early stage concept model, and we can get some numbers from it when we populate all the materials to VEC. What we can also look at this early stage is the contribution that each of these materials has towards the total. My model is conceptual and therefore imprecise, but it's critical we have some idea of carbon footprint from early on, so it can take some informed design decisions. You'll see a more detailed, more granular assessment in the more developed stage when using walls, slabs, doors, windows, essentially when we have a full model. We have components with thicknesses, and that's now the basis on which material quantities are going to be calculated. Apart from a more detailed model, difference at this stage are windows and doors. These objects don't have materials, but they have data fields we need to assess their embodied carbon. Calculation is separated into glazing and frame, so we can enter glazing description as single, double, or triple glazed, and frame material as softwood, hardwood, PVC, aluminium, and composite. Glazed area and frame area are automatically obtained from the window shape and size, so jamb depth and glazing thickness will inform total material quantities. Glazing thickness is total, so 8 mm for a double glazed window means 2 panes of 4 mm. Now let's see this in VEC. We can see windows and doors and the data that is coming directly from object parameters, such as jamb depth, glazing thickness. Glazed area is calculated automatically from the object based on its parametric dimensions, so is the frame area, and EC factor and density values are informed by our input of glazing type and frame material into object's additional data. We can make a change to window parameters, for example, change the glazing from 3 mm to be 6, and then recalculate the worksheet. You can then see how it affects the calculations. Doors are pretty much the same as windows, except they can have no glazing, in which case we'll have 0 as a result here. The calculation is separated into glazing and frame and leaf, as opposed to just glazing and frame. This is assuming that we don't have specific data about windows and doors as products, so we treat them as generic windows and doors. In case we have manufacturers' EPDs for them, we would treat them as single objects. Those would typically be products we have on data as a whole. For example, sanitary ware, which I have in the project and in Resource Manager as symbols. I can attach record format directly to the symbol definition and populate the fields with manufacturer's data from EPD, such as product name and description, weight, embodied carbon factor, sourcing, replacement category, and waste percentage. And then Vec will count how many of these instances I have in my project and give me totals. So what do all these numbers mean? These are the sort of metrics that can back up your informed design choices. To be able to present these to clients and to have a conversation about which strategy and direction to take in order to reduce the carbon footprint of your design. We can look at the results horizontally for a specific material contribution, or we can look vertically and see how much is product manufacturing contributing compared to transport. We have this very useful marionette pie chart, which hooks up to the worksheet and gives us top 10 material contributions to total embodied carbon. Here we just need to bear in mind to enter the total number of materials we input in Vec. We can also change the number of materials that appear on the chart if we want to see top 5 contributors, for example. So what does this tell me? We might want to look at these bricks and concrete as by far the largest contributors and see if there is anything we can to reduce their impact. We can also look at how our performance compares to some targets. In this case, REBA 2030 Climate Challenge, which sets out these targets for 2025 and 2030, as well as business as usual, depending on type of building we are designing. And we need to input here residential, new build offices, or new build schools, and our results will be benchmarked against those targets. So we are somewhere between business as usual and 2025 target. So let's look at our largest contributor, bricks. I'm using standard bricks, but they are being shipped from far away. Now let's change that and have some local bricks instead. We need to recalculate the worksheet and look how much of a difference that makes, bringing us much closer to that 2025 target. We can also update the pie charts and see bricks are no longer the top contributor. Let's just go back for a second to look at the other benchmark in that climate challenge. This is where operational energy comes in, and as I said before, this number comes from Energos as a result of a different process, and I recommend watching energy modeling in the early design stages for full guidance on that particular calculation. So we'll just assume that's been already done and we can just use the results. We only need to create the label under AC Energos and then place it anywhere in the file. I'll just pop it somewhere on this sheet. And in the label settings under performance overview, check primary energy demand. You can see primary energy demand, which is operational energy, now displayed in object info palette as a parameter of the energy label. We only need to recalculate the worksheet to see the operational energy. And we can see it's slightly closer to 2025 target than business as usual. To briefly recap what we've talked about today, you can use native Vectorworks resources to add embodied carbon assessment as a complementary process to your architectural design from the earliest design stages. As the model grows in more detail, as it progresses through the design stages, the calculation becomes more accurate to provide a very powerful way to get the numbers behind your design choices. Pie chart created with Marionette can be used to visualize that data from VEC to make clear the impact of those design choices in terms of the overall carbon footprint. As the conversation about embodied carbon intensifies, we hope VEC provides you with a tool that is easy to use, that is complementary to the architectural design process, allows you to be an active part of that conversation and be able to design more sustainable buildings. This concludes the presentation about embodied carbon assessment in Vectorworks. Thank you for your attention, and I hope you find it useful.